Hey everybody, today we're going to be talking about section 5.2, that is numerical integration. We're going to bust this one up into two pieces because it's rather a long one, plus we have to do a little bit of preliminary stuff. So today we'll do the first half, and then on Monday you can work on the second half. Before we get started with the actual methods for numerical integration, we need a couple of things so that we can build the methods and look at their errors. Okay, so these two topics come from 3.1 and 3.2, deals with interpolating polynomials. Okay, so here's our definition. A function is said to interpolate a set of data points if it passes through those points. Okay, so if a function passes through a known set of data points, we call it an interpolating function. So if we consider these points here, so we have 0, 1, 2, 2, and 3, 4. So you can see here that we can draw a parabola through those points. This parabola is called the interpolating parabola or interpolant, and this gives us a way to create functions given data points. Okay, our goal is to figure out what the equation of this curve is, this parabola. In fact, it comes out to be 1/2 x squared minus 1/2 x plus 1. So how do we get this equation is our goal initially here. Okay, just note one big thing that happens is for any data points that we have, there will always be some polynomial that can interpolate them, as long as the points are distinct. Other functions could also be used instead of polynomials. We could use sine functions or exponentials, but for what we're going to do, polynomials are the easiest to use for our applications. Okay. So how do we get this formula, this polynomial equation? And we use something called Lagrange interpolating, a Lagrange interpolating polynomial. So consider us having a list of points, say x1, y1, all the way to xn, yn. We can get an explicit formula for a polynomial of degree n minus 1 that interpolates the points. We use the Lagrange interpolating formula to do that. Okay? So note one big thing is that the degree of the polynomial that we get is always going to be 1 less than the number of points that we have. So if we have 3 points, like previously, the best we can do for a polynomial interpolant is a degree 2 or lower. If, let's say, we had 5 points, we could form a degree 4 polynomial or less. Okay? So here's an example. Here is the degree 2 Lagrange interpolating polynomial. So this is for our parabola, a degree 2 polynomial, right? You can see it's this ugly formula here, but it's very symmetric. It's not too bad to use, okay? So here, the first term is y1 times this big quotient of a bunch of products, right? So it's x minus x2 times x minus x3. On the bottom, we have basically the same factors, except x1 is substituted in down at the bottom. Second term is similar, so we have the second y-coordinate for the second point times x minus x1 times x minus x3. So you can see that x2 has been omitted here. Same thing for the bottom, so we just evaluate those two factors at x2. And same thing for the third one, okay? So let's think about why this works. So remember that this polynomial should pass through the 3 points that we have to start out with, right? We would have 3 points here if we're dealing with a degree 2 polynomial. So let's look here. So section 5.1. Why does the Lagrange formula work? Well, we want this polynomial to have 3 specific points, right? So for all the x values are our points, we want the y coordinates of our polynomial to be the y-coordinates of our points, right? So let's consider P2 of x1, right? So when we evaluate the polynomial at x1, we're hoping that y1 comes out of it, right? So if we use our formula, we'll have y1 times, again, we're evaluating at x1, so all of our x's will become x1s. So we'll have x1 minus x2 and x1 minus x3 over, downstairs all of these x1s and x2s are known, so these are not variable, they stay the same. x1 minus x3 plus, now the second term here would be y2 times x1 minus x1 and x1 minus x3 over x2 minus x1 times x2 minus x3 plus our last term y3, again we're evaluating at x1, so x1 minus x1, x1 minus x2 over x3 minus x1 times x3 minus x2. So just using the formula there. Again, we've just evaluated this polynomial at x1, so all of the x's become x1. That's it. Now if we notice, let's see what happens here. So here we'll have y1 times something. We'll notice that the factors on the top and the bottom are exactly the same. Therefore, this is simply 1. So we just get a y1 out of this guy. Plus, now if we notice here, this first factor subtracts and gives us 0, and then multiplies the entire thing. So that gives us 0. Plus, same thing happens here. That'll be our 0, right? x1 minus x1 gives us 0. So in fact, P2 of x1 is equal to y1. That's what we're looking for. Similarly, if you do the same thing, P2 of x2 would equal y2, and P2 of x3 would equal y3. Okay. We're not concerned with any other points outside of that because we weren't given them initially. Okay. So you can see here the general formula for an interpolating polynomial. Any degree n minus 1 or less polynomial interpolates a set of data points. This polynomial is this guy right here. So we have the y-coordinate times L1 of x plus y2 times L2 plus yn times Ln, where all of these L's are those quotients here. Okay, so this is just a generalized version of these quotients up here. You can see when L is 1, we get when L is 1, we get our values here. When L is 2, we just substitute in the 2 for our K's here. Okay, so this is just a general version. So you can see that on top we skip over the kth term. If you notice here, we go to xk minus 1 to xk plus 1. We skip over that kth term because we didn't see those in this guy up here. And at the bottom, we just evaluate at the kth value there. Okay. So example 1 has us actually do this problem for the parabola up here. So we want to find the interpolating polynomial. For the points 0, comma, that should say 1, by the way. 0, 1, 2, 2, and 3, 4. Okay. All right, so we're just going to fit it to this formula here. Right, so we have a degree 2 polynomial, so we're going to just use this guy straight away. So P2 of x will equal And be carefully plug in those values for the formula. So our y1 is 1 times x minus x2, which is 2, x minus x3, which is 3, over x1 minus x2, so that would be 0 minus 2, and x1 minus x3, that's 0 minus 3, plus, now for the second term, we're using y2 first, so y2 is 2, times x minus x1, which is 0, and x minus x3, which is 3, over x2 minus x1, x2 minus x3, plus, last term uses our y3, x minus x1, which is 0, and x minus x2, which is 2, over x3 minus x1, and x3 minus x2. Alright, so let's continue to simplify this. So let's see what we get here. We see that on top we'll have to FOIL this out. And here we're going to have 1 over negative 2 times negative 3 is 6. So that's 1/6 times, now let's FOIL this. That'll be x squared minus 5x plus 6. Plus 2 over, let's get our bottom value, 2 times negative 1, which is negative 2. And when we FOIL this, we'll get x squared minus 3x. Plus 4 over, our bottom value here would be 3 times 1, which is 3. And up top, x squared minus 2x. Okay. So let's see what we get. So we'll have a 6th x squared minus 5/6 x plus 1. This is negative 1, so minus x squared plus 3x plus 4/3 x squared minus 8/3 x. Now let's just collect all of our values here. We see, use our calculator, 1 over 6. So I'm collecting all my x squared coefficients here. So 1/6, negative 1, and 4/3. Let's see what we get. And that's exactly 1/2 x squared. Now, negative 5 over 6 plus 3 minus 8/3 is negative 1/2 x, and then our plus 1. So we can see this is exactly equal to the interpolating parabola for those 3 points. Okay. Let's look at example 2. All right, example 2, we want the 3rd degree interpolating polynomial for these 4 points. Okay. So it's a degree 3 polynomial now, so we're going to have more terms involved, right? So degree 3 interpolating polynomial in general will be y1 times x minus x2, x minus x3, x minus x4. Over x1 minus x2, x1 minus x3, and x1 minus x4. Our second term will be y2 times x minus x1, x minus x3, remember we skip, x minus x4 over x2 evaluated there, x2 minus x1, x2 minus x3, x2 minus x4. Our third term, y3, same pattern. So x minus x1, x minus x2, x minus x4, skipping that third term, and x3 minus x1, x3 minus x2, x3 minus x4. And lastly, our fourth value here, x minus x1, x minus x2, x minus x3, and same thing downstairs. So it looks like we've got our work cut out for us as the degree of the polynomial gets larger and larger and larger. So let's fill these in. All right, our y1 is 2 times so 2 times x minus x2, that's 1, x minus x3, 2, x minus x4, which is 3. All over, let's just plug in our x1, so 0 minus 1, 0 minus 2, 0 minus 3. So it's nice that these numbers stay the same. It's kind of a nice feature. y2 is 1, and do it again. So x minus x1, which is 0, x minus x3, which is 2, and x minus x4, that's 3, over 1 minus 0, 1 minus 2, 1 minus 3, plus. Now our y3 term is 0, hooray, so that's going to knock out everything here. If that's 0 multiplied by whatever that is, that's going to be 0. So that's nice, we can move on. y4 is negative 1 times x minus 0, x minus 1, x minus 2, over 3 minus 0, 3 minus 1, 3 minus 2. Right? So let's see what we get. Here we'll have 2 over, now let's see what this is. It's negative 1 times negative 2, which is 2. 2 times negative 3 is negative 6. Times this product here. Alright, so x squared, we'll do the first ones here. X squared minus 3x plus 2 times x minus 3. That's fine. And plus 1 over, let's do this one. 1 times negative 1, that's negative 1. Negative 1 times negative 2 is 2, so that's a half. And this will be x times this product here, x squared minus 5x plus 6. And then our last term would be minus 1 over 3 times 2 is 6. 6 times 1 is 6. That's 6. And our factors, so that will be x times, let's put x there, x times x minus 3x squared minus 3x plus 2. So let's do one more foiling process, then we'll simplify. So I have negative a third times, now let's foil that, x cubed minus 3x squared minus 3x squared plus 9x plus 2x minus 6. Plus, we can get all our terms here, so that would be 1/2 x cubed minus 5/2 x squared plus 3x minus 1/6 x cubed plus 1/2 x squared minus 1/3 x. Alright, so let's go and collect all of our terms here. Do one more simplification, I guess. So let's say we'll have negative 1/3 x to the third. Now here we'll have negative 6 x squared times negative 1/3 gives us 2 x squared. Here we'll have 11 x's, so that would be negative 11/3 x. And then positive 2, plus the rest. All right, now let's go collect our coefficients. So negative 1/3 plus 1/2 plus negative 1/6. So that is 0. Two x squared, so 2 minus 5/2 plus 1/2 is 0. Negative 11/3x plus 3 minus 1/3 is negative 1, so that's negative x plus 2. So here we have the degree 3 polynomial is simply this line because of the cancellation that occurs. Okay. Now, let's talk about the interpolating error. As I said before, this polynomial does not necessarily have to be degree 3. It could be less than that. And that comes from having maybe zeros as our y values or some cancellation happening when we simplify this. Okay. Now, let's talk about the error of interpolation. Okay, so the interpolating error is defined to be at a particular x value, the difference between the function and the interpolating polynomial, or the difference in the original function and the interpolating polynomial. So for various x values that are not within our data set, that's what we're concerned with, finding the error for. So if we consider adding a data point to the original list, after we have found the interpolating polynomial, we then will find the error by subtracting the actual function value from the value obtained by the interpolating polynomial. The interpolating error, there's a theorem for that, which I won't prove here. It's just a little bit too complicated for what we're doing. But here it is. The interpolating error using some Taylor polynomials can be found to be this quantity here. So it's x minus x1, x minus x2, all the way up to x minus xn over n factorial times the nth derivative of f at c, where c is between the highest and lowest values of x1 to xn. This will be important when we get into our errors for numerical integration techniques. Okay. So let's take a look at a few of the integration techniques that we'll be dealing with here. Okay. You may have remembered from a calculus class, maybe possibly using some of these techniques. So the definite integral, the calculation for that, we know relies primarily on interpolating polynomials. So if we consider some function defined on a to b, that is not easy to integrate, right? We can't do an integral analytically for it. We use these approximating techniques using these interpolating polynomials to get the integral, right? So if we draw the interpolating polynomial for some points of f of x, because the polynomial is easily anti-differentiated, or we can use that polynomial to approximate the integral of f of x. Okay. So for various formulas called Newton-Cotes formulas, these are the following. So the trapezoidal rule, Simpson's rule, and the midpoint rule. And then there are composite methods for each. We'll talk about those next time. Okay. So we'll look at the trapezoidal rule and Simpson's rule in this video. Then we'll take care of the others next time. Okay. Before we get started, we want to look at a few integrals that pop up within our discussion of the derivation of these methods. Okay? And those graphs for those integrals are given here. So you can see here we're looking for the integral under the definite integral from 0 to h for this line. Here we're looking at the integral negative h to h for this parabola, and then the integral negative h to h for this parabola. So if we look here, we see that this is the degree 1 interpolating polynomial for the points 0, 0, and h comma 1. Okay, so that will give us x over h as the interpolating polynomial. We can see that here. So integral a. So p1 of x then is y1 times x minus x2 over x1 minus x2 plus y2 times x minus x1 over x2 minus x1. So that's the Lagrange formula for our degree 1 interpolating polynomial. If we do that, plugging in those points, we get 0 for our y1, so that's just 0. Plus y2 is 1 times x minus x1, which is 0, over x2 minus x1, which is h minus 0. So that's x over h. Okay. And that's what we have here. Okay. So looking at the integral from 0 to h of x over h dx is then, this is just a constant, right? So 1 over h times the antiderivative of x, which is 1/2 x squared, from 0 to h, is, let's see, 1 over 2h times h squared minus 0, or h over 2. So that's our result here. Here we have the second one. It's the interpolating polynomial for our parabola, which is the integral from negative h to h of whatever our formula is, dx, which is this antiderivative evaluated from negative h to h. Should give us 4/3 h. Okay. So let's just show that. So p2 of x here will be, using our formula previously, it will be y1, which is 0, which is nice, plus y2, which is 1, times x minus x1, which is negative h, so plus h, and x minus x3, which is h, over x2 minus x1, x2 minus xh, plus y3, which is 0 again, which is nice, right? So let's see what we get. That would be down at the bottom, we'll have negative h squared, so negative 1 over h squared, times the top, which is difference of squares, it's x squared minus h squared. Or negative x squared over h squared plus 1. So the integral from negative h to h of this function is the integral from negative h to h of this guy here. Which is negative x cubed over 3h squared plus x. Note that h is constant, so we just increase and divide. Look at this. Antiderivative of 1 is x, negative h to h. All right, evaluating that, we get negative h cubed over 3h squared plus h minus negative h cubed, so that's going to be positive, h cubed over 3h squared minus h. So we see this is exactly the same integral if we change those signs, right? Plus, minus, plus. These can actually be reduced to negative h over 3 plus h minus h over 3 plus h. And to take away 2/3 is 4/3, so 4/3 h. The last problem is you will show this for homework. All right, so now we'll look at the first method of numerical integration, called the trapezoidal rule. You may have remembered this if you took a course in high school doing calculus. What the trapezoidal rule does basically uses a trapezoid to estimate the area underneath of a curve. Of course, this is just an approximation. So as you can see here, we have this function f. It's known, 2 points on f are known, and we approximate the area under f by using the area of this trapezoid. Okay? You can see this approximation is not too good, but if the distance between x0 and x1 is relatively small, it actually becomes a pretty good approximation to our area that we're looking for. Okay? So here it is. Here's the trapezoidal rule. It says that the integral from x0 to x1 of some f of x dx is equal to this term here minus h to the third over 12 times f double prime. This will be the error of our approximation. Okay? So let's go through the derivation of that particular method. Okay? Trapezoidal rule. All right, so once again, trapezoidal rule uses a degree 1 interpolating polynomial to approximate this area, right? Degree 1 polynomial is a line, so that's what we're using here, okay? So f of x can be an interpolating polynomial for f of x can be created. That would be p1 of x plus some error term, right? Plus some error term. So p1 we've seen before is y1 times x minus x1 over x naught minus x1 plus, well, let's use y naught here, y naught. And then y1 is x minus x naught over x1 minus x naught plus our error term. Recall previously the error term for a polynomial interpolating function is given by this here, right? So here we would have x minus x naught, x minus x1 over n, which is the number of points that we have. That would be 2 factorial times f double prime at c. All right, so let's look at integrating the first portion of this. So I'm going to integrate both sides from x naught to x1. So the integral from x naught to x1 of f of x dx is equal to the integral of this portion plus the integral of our error term. All right, so looking at this first integral here, we can actually break this up into 2 separate pieces. So let's do that. X1, Y1. So just this first portion here. Okay. So again, we're just looking at the first integral of the polynomial portion here. Okay. So based on our previous results, we see that this is just the interpolant for some line. So we should see that this is going to be equal to y naught times x one minus x naught over 2 plus this guy is going to yield y1 times x1 minus x0 over 2. Okay. This is coming from that first formula. So here, we can actually condense that. It should be 2 plus y1 times h over 2, where h is equal to x1 minus x0. Okay, so again, this result stems from here, our first integral that we calculated previously. It has the same form if we consider that. We could have also just gone through and gotten this, because this is not too bad of an integral to calculate. So we can see that. Now for the integral of our error term, this integral of the error term here is equal to integral from x0 to x1 of our error term, x minus x0, x minus x1 over 2 factorial, and f double prime of c dx. So here, note that f double prime of c and 2 factorial are constant, so we can pull those out. F double prime of c over 2 factorial times this integral. This integral is not too bad to calculate. But if we do, we'll see that this becomes 2 factorial. If we make actually go through and do this, we would get negative h cubed over 12. Okay. Which is, over 6. All right, you can see this one in the second integral, part B, that we did. So our error term is h cubed over 12, f double prime of c. So here we get this is the upper bound of the error for our approximation. So, thus, the formula for the trapezoidal rule is the integral from x0 to x1 of f is equal to the integral for p of x, which was y 0 h over 2 plus y1 h over 2 plus our error integral, which was negative h cubed over 12 f double prime at c. We could actually get this in a more compact form because we have the common factor h over 2 here, so h over 2 y0 plus y1 minus our error. Okay, that gives us exactly what we have here. All right. We'll be using this in just a minute. Let's look at Simpson's rule. We can do this in a similar fashion, except we use a degree 2 polynomial to do the interpolation. Okay, so in the trapezoidal rule, we use a line between 2 points. In the Simpson's rule, instead of using that line, we use a parabola. So a second degree polynomial. So we look at 3 points on the function, draw a parabola between them, and estimate the area that way. So you can see here that this would give us a better approximation to the area for this function if we use the Simpson's rule. So here Simpson's rule gives this formula here, which we can derive in a similar way. So Simpson's rule. Suppose we have 3 points, x1, y1, x2, y2, and x3, y3. Well, let's do not. So x naught, y naught, and then 1 and 2 instead. Alright, so we have these 3 points for our interpolating polynomial. So that interpolating polynomial, f of x, can be interpolated by doing y naught times x minus x1, x minus x2, over x naught minus x1, x naught minus x2. Plus our second term, plus our third term, plus the error term here. So the error term would be x minus x1, x minus x2, x minus x3 over, we have 3 points, 3 factorial, times f triple prime at c. Or you could say p of x plus an error. Right? So it's our f of x is equal to the polynomial interpolant plus some error term. Okay. So the integral from x naught to x2 this time, we're going to x2, f of x dx is equal to the integral from x naught to x2 of p plus the integral from x naught to x2 of e. So what we need to do is integrate each of these terms, and we can do so in a previous fashion. This will end up, this guy here, integral of this first term is equivalent to y naught h over 3 plus y1 times 4/3 h plus y2 times h over 3. Plus, our error term ends up being negative h to the 5th over 90 f quadruple prime of c. Or, you can factor out h to the 3rd here, h to the 3rd, y naught, plus 4y1s, plus y2, minus this error term. Again, all of the derivatives, antiderivatives of these flow from the three that we did previously today. Okay. So let's look at our last example. So we want to apply trapezoidal rule and Simpson's rule to the integral from 1 to 2 of the natural log of x dx, and find an upper bound on the error. So let's first do our trapezoidal rule. Trapezoidal rule says that the integral from 1 to 2 of the natural log of x dx is equal to, so let's go back, it would be h over 2 times y naught plus y1. This is approximation, right? Approximation. So recall that h is defined as x1 minus x naught over 2. So all we need to do is evaluate the function, or have the x values that we're concerned with, here and here, and then evaluate the function at both of those. So 2 minus 1 over 2 times the natural log of 2 plus the natural log of 1. 2 minus 1 is 1, so that's a half. Natural log of 2 plus natural log of 1 is 0. So we get 1/2 times the natural log of 2. This is approximately equal to 0.3466. Okay. As for the error, we know we calculate the error by doing h to the third over 12 times f double prime at c. So we would need the second derivative of the natural log function. We know the first derivative is 1 over x. The second derivative is negative 1 over x squared. So here we see we'll have 2 minus 1 to the third over 12 times negative 1 over c squared, or negative 1 over 12 c squared. Excuse me, this should be minus, right? Minus, so it's minus and plus. All right. So the upper bound for our value here would be the value that makes the largest possible error based on our endpoints. So the error bound would be less than or equal to 1 over 12 times 1 squared, or 1/12. For Simpson's rule, we know that the integral from 1 to 2 of natural log of x dx is approximated by h over 3 times y naught plus 4y1 plus y2 minus, well, we'll take care of that in a bit, okay? So h again is, remember, x2 minus x1. So in this case, h is now 0.5, right? So again, we're going 1 to 2, but we must use 3 points, so we have to use 1.5. So h is 0.5 this time. Okay? 5 over 3 times the natural log of 1 plus the 4 times the natural log at 1.5 plus the natural log at 2. This is approximately equal to 0.3858. For error, Simpson's rule says our error is negative h to the 5th over 90 times f quadruple prime at c. So we know f was the natural log of x, f double prime was negative 1 over x squared, so f triple prime is 2 over x to the 3rd, and quadruple prime would give us negative 6 over x to the 4th. So here we have negative 0.5 to the 5th over 90 times negative 6 over x to the c to the 4th in this case. This is less than or equal to, when c is 1, we're going to get negative, so that would be positive 0.5 to the 5th times 6 over 90, which is 0.0021. So Simpson's rule tells us that the integral from 1 to 2 of the natural log of x dx is equal to 0.3858 plus or minus this value here. Okay? So we've gotten a better approximation than the trapezoidal rule. Okay? All right, so you should now be able to do the homework exercises for this section. Here we have one exercise coming from section 3.1. 2 is to show that the integral from part C of our notes was true. That's this guy. Here, so show that this is true based off of this graph there. And then last, using the trapezoidal and Simpson's rule, like we've just done, to approximate these antiderivatives. If you have any questions, please feel free to email them to me.